Hello everyone. Today we are reviewing a NeurIPS 2021 paper, ATISS, Autoregressive Transformers for Indoor Synthesis. The full title is a mouthful, so I'll just call it ATISS from here on. This paper tackles one fundamental question. Given just the floor plan of an empty room, can we automatically place furniture in a way that looks realistic and natural? But ATISS doesn't stop at scene generation. The really interesting part is that a single model handles 5 different interactive tasks: full generation, scene completion, object suggestion, constraint placement, and even automatically catching and fixing misplaced objects. You can see across all 4 room types here. The layouts look genuinely human-made. Before ATISS synthesis went in 3 main directions, and each one had a serious limitation. First, precision modeling. You literally write down rules for how scenes should be built. The problem is that writing those rules takes deep domain expertise and a lot of time. Second, scene graph based methods. These works, but they need extra annotations, explicit glyphs describing the relationships between objects. That data is expensive to collect. Third, autoregressive CNS or transformers that place objects one at a time. The catch is you have to impose an arbitrary order, say left to right or um, biggest first, but that order doesn't actually exist in the data. So if a real combination like a common bed appearing after a rare ottoman never shows up in training, the model just never learns it. ATISS serves all of these with one core idea: treat the scene as an unordered set, not a sequence. Follow the ideas through to its conclusion, and you end up with the beautifully simple design. A transformer without functional encoding plus chain law attributed decomposition plus mixture of logistics output. That's basically the whole paper. Let's get into the method. A scene S is just a flow layout F plus an unordered set of objects O. Each object is a 3D bounding box defined by 4 attributes: category, translation, size, and orientation. The crucial part: there is no inherent ordering between objects. If we factor the joint likelihood with the chain rule, we'd get we get equation 1, the probability of the jth object conditioned on all the previous ones, where phi is a function that defines on ordering. The full scene low likelihood for that ordering is just the equation of 2, the sum of those conditional terms. Standard autoregressive decomposition so far, but but there are two problems with this setup. First, the number of possible ordering is m factorial, completely intractable. With just 10 objects, that's already 30.6 million orderings. Second, and this is the deeper point, we want the model to give us good results no matter what other object come in. Optimizing a single ordering's likelihood doesn't guarantee that. So ATISS defines the objective as equation 3, maximize the average log likelihood over all possible orderings. Computing m factorial terms every step is obviously impossible. So in practice, we sample one random permutation and only optimize that one's likelihood. Why is it valid? 2 steps. First, by Jensen's inequality, the average log likelihood is lower bound on the true set log likelihood. Second, and this is the key. If we make the transformer permutation invariant by removing positional encoding, every ordering gives exactly the same likelihood value. That means the lower bound becomes tight. So one ordering's likelihood equals the average equals the true set likelihood, which makes one random permutation and unbiased gradient estimator. That's the heart of the paper. Each object is a 4-tuple CTSR, all defined in the room's normalized local coordinate system. T is translation, specifically the center point of the bounding box measured from the room origin. S is the size, stored as half extends in the object's local axis before any rotation is applied. All is the orientation, but only yo. Rotation around the up axis, pitch and lower or pitch and lower assumed 0. Since furniture pretty much always stands upright. Category is 1/2. Everything continuous T, S, and R is modeled with a mixture of logistics, or MOL for short. Why MOL? 3 regions. First, furniture placement is inherently multimodal. Take a bed, in a rectangular room. It can plausibly go against any of the four walls that gives a position distribution with the four distinct peaks. If you regress this with a single Gaussian, the mean would collapse to the middle of the room, not touching any wall. That mode collapsed, and it's exactly the failure mode of earlier methods. Second, the logistic CDF is exactly the sigmoid function, beautifully closed form. Let's just use discretized logistic likelihood, which computes probability via CDF differences. Though PDF blow-ups very stable training. Third, and this is a smaller point, is the proven recipe from Pixels and N++ and WaveNet, battle tested. The model has four components. One, the, the layer encoder extracts features from the room shape. Two, the structure encoder embeds context object. Three, the transformer encoder predicts the next object. Four, the attribute extractor decodes the actual attribute values. The layout encoder extracts the layout encoder takes the top-down image of the floor plan, runs it through ResNet 18, and produces a 64-dimensional feature. The structure encoder embeds each object four attributes separately and then sums them to form a context embedding C. Category goes through a low-level embedding. The continuous attributes go through sinusoidal positional encoding and then MLP. Worth noting, here positional encoding is being used to encoding the value itself, not the sequence position. Same trick, different purpose. The transformer input is a single bag of tokens. The layout feature all context object embeddings and the learnable query token Q. The Q token plays the same role as Burt's mask token or VIT's class token. It asks what's the next object. Here's the key design choice. The sequence positional encoding. That single decision makes self-attention permutation equivariant. The model treats inputs as a real set, and that's what justifies the random permutation training we just talked about. Predicting attributes happens via channel decomposition in the order category, translation, size, orientation. Each NLP head is conditioned on all previous attributes. Category is k plus one way categorical. The extra place is the end of scene token. The rest output MOL parameters, mixture weight means and log scales. Disordered flow follows a natural causal flow. What kind of object? Where to put it? How big? And finally how to locate it. Big category objects also have narrower position distributions, so predicting them first reduces the variance. Every step sample a scene, apply a random permutation, pick a random prefix length t, and predict the t plus 1 object using NLL laws. When t equals m, the target is the end of scene token. Start with an empty context, then autoregressively sample category, position, size, and orientation, appending each new object until the end token appears. The actual 3D meshes aren't generated. They are retrieved from the 3D feature library by matching bounding box dimensions. That the triple trick is one of the legion's inferences so fast. One model, 5 tasks, all from the same weight. No fine-tuning needed. Scene completion, fit in partial scene, sample until end. Object suggestion, sample one step, stop. Constraint placement, fix the category, sample one, position, size, and rotation. Rearrangement, mask positions and resample. Failure correction, rank objects by log likelihood, find low probability ones and resample them. All of this works because random permutation training automatically taught the model the conditional for every possible subset of objects. On 3D prompt across 4 room types. ATISS builds informer fast scenes and sync to gen on every metric, FID, KID, and scene classification accuracy, and the inference is up to 8 times faster. The big takeaway, 3 simple design choices: no positional encoding, chain rule, decomposition, miserable logistics, Give a straight over the art quality, 8 times the speed, and 5 interactive tasks for the price of one model. A beautiful example of how the right framing can make complexity disappear. That's it for the artist review. Thanks for watching.